Hey guys, this is a lecture on number theory, and it's going to be accompanying a stream, and that stream will have. There's also like some practice problems that go with it, so you can test out the concepts that you might learn here. And then later on, in a couple of days, there'll be a stream, and I'll take questions and go over the solutions to these problems. The stream is probably going to be at an unusual time. It's not going to be on the weekend. It'll be like Tuesday or something. This was mostly to avoid conflicts, but you can find the exact time in the description. So this is long enough that I made it a slideshow because my hand is going to die if I try and draw everything out. And it's going to be even longer if I try and draw anything out, so I'm just going for more compressed format. And I'm also sure I missed some stuff, so if you know something obvious that I missed, feel free to bring it up. I'll talk about it. And yeah, so here you can see a tip. For a pretty big part of number theory, it just sort of helps to think of it like explicitly. Like you want an explicit equation, or you want some specific condition to be satisfied. And then with that equation, that gives you something like solid that you can mess around with. And you can mess around with an equation, and you can mess around with it so it becomes something that's easier and something you know how to solve. Because we can solve certain forms of equations, we can solve certain requirements. So if it's something you don't know, maybe you should try to turn it into something you do know. So briefly, I'll talk about floor and ceiling, which is really simple. Floor is just the number rounded down. So 2.5 rounded down is 2. If it's an integer already, it doesn't get rounded. It doesn't like go down. So 2 rounded down is still 2. And then ceiling is rounded up. And so 2.5 rounds up to 3. These show up a lot in beginner problems, so I think it's good to mention. Okay, so a bit of background on divisors, because they're going to be important in number theory too. A brief definition is just that if A is a divisor of B, then B modulo A is 0. And we'll get to modulo later, and it might be kind of no, it won't be circular. I'll define modulo later, but thinking about divisors like that will help you model it as an equation, like I've said before, and it'll help you think about problems like more explicitly. But I mean, I'm sure you have a general idea of what a divisor is overall. So some notation as well. A bar B means A divides B. So A is a divisor of B, or B is divisible by A. And so a divisor is a number that divides another number. It's also transitive. So if you have A dividing B and B dividing C, then A divides C. This should be pretty intuitive. And another brief definition of a prime: it has no divisors except one in itself. And prime factorization, if you do that to a number, it basically means you're breaking it down into the primes that like multiply to it. And because primes are primes by definition, they can't be broken down any further because they don't have any more divisors. But like 2, for example, is prime, so its only prime divisor is 2. 10 can be broken down to 2 times 5, both of which are 5. And that big number can be broken into a bunch of different primes. It's also worth noting that a prime factorization is broken down as far as possible. So 3 times 9 is not valid because 9 is also able to be broken down into 3 times 3. So we're going to start with prime factorization, and just like, what are the algorithms? The goal is to break x down into its prime divisors. The first thing is naive. You can try all the numbers and then see what divides it. And then when you find a number that divides it, you can divide x by that and then keep trying numbers. A bit less naive is you can only try the primes, and you can pre-compute the primes beforehand, but it doesn't really help that much. Only like a log factor. And even better, you cannot have 2 primes larger than square root x, because if you did, then like you'd have 2 bigger's larger than the square root, so that squared number would be larger than x. So if you've tried all the primes less than square root x, then the only primes you haven't tried are larger, and you can't have 2 primes that are larger, so x has to be prime, because there's no way that it can be at least 2 primes. So this reduces the complexity to square root x over log x to do prime factorization. And the reason is that like there's just some math that shows that the average distance between primes is logarithmic. Like the average distance between 2 primes that are on the order of n is around log n. Or a different way of thinking about it is from 1 to n, you're expected to have like n over log n primes. It's just there's some math that says that. So the overall complexity is square root x because you only go up to square root, and then divide that by log because you're only trying prime numbers. Code for doing this is here. I think it's commented pretty well. And there's some more algorithms like Pollard's row, for example. I'm not going to cover those here because I don't exactly know them, but there's a link in the description for that. And also a link in the description for actual code that works really well. And that would be what I copy paste if I'm having time issues. Another thing is finding divisors, which like prime divisors are only the primes, but like divisors are anything. So even though 10 isn't prime, it's still a divisor of 20. Now, one thing to note is if you know something is a divisor, then like if you know y is a divisor of x, then x over y is also a divisor, just because x is divisible by y. So x over y is like an integer, and x over y times y is equal to x. So you know that x over y is a divisor, and it's an integer. So you only have to check up the square root x, and then the rest of them will come from also including x over y. So overall, that complexity is similar. It's square root x. Something else you can do is prime factorizing it, and then you can generate the divisors from that. And generally, that's faster. So I guess that's to be recommended, because it works in O of number. It works in like every divisor takes up 1 unit of complexity if prime factorization is fast enough. So it's mostly the prime factorization that will dominate the complexity. But the other algorithms that I haven't mentioned can actually do it pretty quickly. Next thing to talk about is modulo. Imagine like dividing imagine dividing 17 by 6. You can subtract 6 twice, and then you're left with 5. And so the modulo is sort of this like remainder. It's what you're left with after you can't subtract 6 anymore. So 17 modulo 6 is 5 because you have 5 left over. And the math sort of requires that this has to be between 0 and that like number. But so that also means it can't be negative. So 17 mod 6 is, you can think of it like basically repeated subtraction or repeated addition. For 17 mod 6, you just subtract 6 until it becomes small enough. And for negative 15 mod 6, you add 6 until it becomes large enough. So another way to think about numbers that helps with modulo is thinking of like this x equals am plus b. So for example, we're thinking in terms of 17 mod 6. So we can write 17 as 2 times 6 plus 5. So that the number a is x divided by m, and the number b is x modulo m. And so negative 15 is negative 3 times 6 plus 3. And we also give the same constraints on the number b that we do on modulo, that it has to be between 0 inclusive and m exclusive. So this is nice because when we do mod, am is just a multiple of n, so we can just get rid of it, and we don't care. So when we take x mod m, all we're left with is b. So am plus b mod m is just b. There's also a special note for C++ that modding with negative numbers might also give you a negative number. It'll be very close to the number you want, but it could be negative, so be careful about that. Now, just to like sort of ingrain this this representation of a number in your head, because remember the representation is like it's some amount of m's and then you get like a remainder at the end. So thinking about numbers like that, try and prove the basic identities for modular arithmetic, that you can mod as many times as you want and wherever you want, and it's not going to change the result. So for example, a plus b mod m is equal to a mod m plus b mod m all mod m, because you can mod as much as you want in between. And yeah, there's also division that is not mentioned here, and that will be more complicated, so I'll get to that later. Anyway, you can feel free to pause the video and do that. So I'll do the hardest one, the rest follow more easily. So we'll expand out the left and right side and show that they're equal. So first we say that A is equal to Cm plus D, this representation, and B is equal to Em plus F. So we will compute the left side first. So we get this expression, we expand it out, and then everything except for the term df is a multiple of m. So because we're modding, we just get rid of it, and we just end up with df. And then the other side, the m terms go away immediately, so we just end up with df anyway. And so because the left side is the right side, we've done it. You can do the same with addition and subtraction. A couple other things you can do for modulo is binary exponentiation, where you want to compute like a huge power of some number quickly. And so for example, for like 21, what you would do is you would write it in binary as hinted by the name. And then you have, I did do a tutorial on bitwise operations previously that could help in understanding this. But basically 21 is 16, 2 to the 4th, plus 4, 2 to the 2, plus 1, 2 to the 0. So we're going to take all those 1 bits and like make a list of them. And then, so we'll write a to the 21 as a to the 1 times a to the 4 times a to the 16. And because a to like the 2x is just a to the x squared, we can find a to the x and then we can find a to the 2x like immediately. So we can compute the sequence of a to the 1, a to the 2, a to the 4, a to the 8, etc. all in like O of 1 each time, and they're log terms total. And then we just take the ones that we're interested in. So here we would take a to the 1, a to the 4, a to the 16, product them together, and we win. Total complexity is log b because it's the number of bits in b. It is a bit more complicated when you're taking this caret, the triangle, the thing that's pointing up, is also exponentiation, by the way. So this term is a to the b to the c. So a to the b to the c mod m is kind of complicated because you cannot, it's not right if you take b to the c also mod m. It turns out you have to do it with like it can't be mod m, but you can do it with something called the totient function. And that's just because like you can sort of prove that a to the totient will become 1. And so it means you can subtract or add out the totient as much as you want and it won't change the answer, and that's what modulo happens to be. So in the case of like 10 to the 9th plus 7, which is a common mod, or any prime, the totient function is just that number minus 1. So here you can compute b to the c modulo 10 to the 9th plus 6, and then you can compute a modulo that like modded exponent. See the description for more. And also logarithm is like, discrete log is weird. I don't know about it. I'm not going to talk about it here. Now I did mention division before. You can see the first line just says weird, and it is. And it might sort of require you to rethink what you think of as division. Because division is really just the inverse of multiplication. Like 5 times 1/5 is 1, right? So 1/5 is, by definition, the number that when you multiply it by 5, you get 1. So 1 over x, otherwise known as x to the negative 1, is the y, the number y, such that x times y is equal to 1 when modded by m. The problem is sometimes it doesn't exist. For example, try and take the inverse of 2 mod 4. It doesn't exist. You can try all the numbers, it doesn't work. And so it turns out it only exists if the greatest common divisor of x and the modulo is 1. And I will explain GCD like right after this, but basically that's how that works. That otherwise, like, because x and m are both divisible by that number will be in the x times y factor, whatever you do. And so that means it cannot be 1 because you can't both be 1 and be divisible by some number larger than 1. So it just doesn't exist in this case. And otherwise, you can show that it does exist. So the computation of a modular inverse is not it's doable when it exists. And otherwise, it doesn't exist, so it's fine. So if m is prime, there's a like cool little trick you can do. There is a theorem that says, remember the totient function, like computing it 10 to the 9th plus 6? This is sort of related to that theorem. Where it's basically saying for any a, if the modulo is something, if m is prime, then a to the m minus 1 is going to be equal to 1. I linked the proof in the description. I'm not going to do it here because this video is long. So with that equation, if you believe it's true, divide both sides by a, and that's it. A to the negative 1 is equal to a to the m minus 2. So you just need to take a to the m minus 2, and I just showed you how to do binary exponentiation, so you can do that in log m, and therefore everything is great. If x and m have no greatest common divisor, if they're coprime or if their GCD is 1, then there's another algorithm that can do it. It's called the extended Euclidean algorithm. I will cover that shortly. But because primes are coprime to everything except itself and like multiples of it, the coprime case will also cover the prime case no matter what. So you don't need the prime case if you know the coprime case. So next part of this lecture is GCD. It's essentially the greatest common divisor. And it is what it says. It is the largest number that divides both x and y simultaneously. If you think about it in terms of prime factors, for example, you write x as you write 12 as 2 to the 2 times 3, and you write 18 as 2 times 3 squared. Then the GCD will be like, if you consider only the 2's, it'll be the smallest exponent. So for example, the GCD of 12 and 18, the 2 factor is just a single 2, because it's the GCD of 2 to the 2 times 3 and 2 times 3 to the 2, and the smallest exponent in that is 1. The 3 factor will also be 1 because there's a 1 in the exponent of 12 for 3. Probably helps to do some examples out for that. But like break it into the decomposition of like prime factors and then prime powers specifically, like powers of 2, powers of 3, powers of 5, powers of primes, instead of just 2 times 2 times 2. And then you can sort of get a different understanding of how GCD works. The way we compute GCD uses a thing called the Euclidean algorithm, and I just did mention the extended Euclidean algorithm, so we'll get to both of those, maybe. And another thing to mention, if you want the GCD of like a list of numbers, you can just do 2 at a time, and then use the results of the first 2 on the third, and so on. Because any number that divides like all of them can be like iteratively deduced. So Euclidean GCD. This is the Euclidean algorithm. It relies on the fact that the GCD of 2 numbers, specifically a and b, is equal to the GCD of a minus b and b. We're assuming a is greater than or equal to b, if not, swap them. But the reason this is true is because if you have because both a and b are divisible by the GCD. So we're saying that a mod g is 0 and b mod g is 0. So then, therefore, a minus b mod g, we can use the identity you might have derived before to say that a minus b mod g is a mod g minus b mod g, which are both 0, and so the whole thing is 0. So a minus b mod g is 0, and by that definition, that means g is also divisor of a minus b. So that shows that you won't lose any divisors by subtracting b. And you can also show you won't gain any divisors. It's much clearer than this. You can just do some casework on like what if g divides a, or if it divides b, or if it divides neither. And you can show that you won't get any like new divisors. We also know that modulo is repeated subtraction. So the GCD of a and b is actually the GCD of a modulo b and b, not just a minus, because we can subtract as much as we want. And then because we want to maintain that a is greater than or equal to b, a mod b is going to be less than b, so then we swap them so we continue the algorithm. And then the base case for this is if you have GCD of some number in 0, then that's like the GCD of anything in 0 is itself. So the GCD of x in 0 is x. The proof that this algorithm works is that a mod b will always have the number, and therefore Like a mod b will always be less than or equal to a over 2 if a is not less than b. And so the value of a will half every time. And so the complexity is also logarithmic because you're halving the numbers. A definition is that two numbers are coprime if their GCD is 1. Or it's also relatively prime. I think they mean the same thing. Coprimality will come up later as well. So this is an example. We do 133, which is 7 times 19, and 56, which is 8 times 7. So 133 and 56, we swap them, take 133 mod 56, which is 21. Then we need to compute this part, so we do it again. 56 mod 21 is 14, so we go here. We do this again. 21 mod 14 is 7, so we get this. We do it again. We get 7 and 0, and that's the base case. And the code is like this. It is very simple. You can also do it iteratively. It doesn't really matter. I think iteratively might be a bit faster, but I'm not really sure. There's also the extended Euclidean algorithm, as I mentioned before, but I don't actually I've seen examples of it, and I can kind of understand how it's derived, but I don't really understand enough to explain it well. So I'm sorry for that, but basically what it does is it solves the equation ax plus by is equal to 1 if a and b are coprime. But if they aren't coprime, then the equation it will actually solve is where ax plus by is equal to GCD. And there's this thing called Bézou's identity, not sure how to pronounce that name, but it says that the solution pair xy will always exist. So that's cool. And there's more info in the description on that, but the basic idea is to run GCD backwards. You do this whole thing to get the numbers, and you can find the GCD this way. And you can also, the way the algorithm works is that it builds upon the numbers you use, and then you can work backwards and reverse engineer the values of x and y like that. But I don't know enough to explain it. So I mentioned before you can use it for modular inverse. So for example, you want to solve the equation cz mod m is equal to 1, and you want to figure out what z should be. And you know what c is, and you know what m is. And also c and m have to be coprime. So basically, you just plug it right into extended Euclidean. You set a equal to c, and you set b equal to m. So you're really solving the equation cx plus my equals 1. And notice that my is essentially, y can be any integer. So you can basically add or subtract the value m as much as you want, which is exactly what modulo is. But another way to think about it is you solve this equation, you take the final result modulo m, and then the my just goes away. So you just get cx mod m is equal to 1. And that's you just solved that. And you know what x is. So that's your answer. So because it's reverse engineering GCD, the number of steps it'll take is around the same. So it's also log of the minimum of the two arguments. Another brief thing, the least common multiple. It's the smallest number that's a multiple of two numbers. So the LCM is the opposite of the GCD. If you think about the prime powers, it'll be the maximum of each individual power. So the LCM is one way to get it is you take the multiples and then you divide the GCD. And the reason this works is because the GCD is a divisor of both of them, you shouldn't include it twice, because when you include it once, it's already there and you don't need any more of it. And everything else, you have to include it because it's only in one of them. So you won't include it twice because it's only included in one of them. And so overall, you include all of the multiples you need exactly once, and you don't need the GCD twice because you can take out one of them. And because both numbers have it, then you'll still have the GCD there. That's kind of what I'm trying to say. I guess. I don't know. Alright, let's go to something else. There's something called the Chinese remainder theorem, which is kind of useful. And it says that basically the most basic form, you have four numbers, a, b, x, and y. And it says that there is a unique, not necessarily unique, but on the interval from 0 to a times b, there's a unique solution. No, sorry. The interval from 0 to x times y, that there's a unique solution to these two equations. Z mod x equals A and Z mod y equals B. What I'm saying is unique if you take Z modulo, I believe the LCM of x and y, or because they're co-prime, there's a unique Z if you take it modulo x times y. Also, x and y do have to be co-prime, and that will be relevant. So it says that there's a unique Z modulo x times y that satisfies these equations. But it's also not restricted to just these two equations. Like you can plug it in for 3 or 4 or infinite equations. As long as all of the numbers are co-prime with respect to each other, then you can have as many equations as you want. Or specifically all of the mods. So if it's not co-prime, it can be invalid because, like, for example, say you want a number which is 1 mod 4 and is 0 mod 6. That means it has to be both even and odd if you think about it, which is clearly dumb. So this theorem says it exists, which is cool, but sometimes we need this number. And so the question is, how would you derive a way to find this Z? How would you find it? I'm asking you to find it. How would you find it in better than O of x and O of y? And I'm guaranteeing you that I've covered all of the stuff that you need to derive it in this video already. Like, up to this point, I've already covered everything that you need. So you can try it. You can pause the video and try and figure out how you would do it. And I'll give you a couple of hints in the next few seconds, so you can pause right now. And yeah, we want complexity better than O of x or O of y, because otherwise we can just brute force it. So let's not do that. Go ahead. So the first hint is equations. We want to set up equations, as I said, the tip in the beginning. So let's think about the modulo form that we went over before. We're thinking of everything in terms of m, so we're writing x as am plus b, and b is equal to x mod m. Note that we are writing the modulo x in terms of am plus b. Actually, I shouldn't say that. You can do whatever you want with it. It's not necessarily the modulo. It's just, yeah, I'm kind of confusing myself with my own notation, actually. Just think about this form and see how you can apply it here to anything. Not necessarily to the modulo itself, because that doesn't actually make sense. Now apply that, mess around with the formulas, see what you can do. Second hint coming in 3, 2, 1. Now, what you're trying to do is to reduce it to an algorithm, which I have covered in this video. So look through the video and see what algorithms you can find that runs in log of min and x and y. And the reason it's minimum is because, like, if you can just take the smaller one and run it on that. It only depends on one of the variables, and you can run it on whichever one is smaller. And note that it is an algorithm and not a formula, because I don't think there's a formula that will directly give you the answer in like O of 1. So solution in 3, 2, 1. Now, let's look at the case with only 2 equations, just for simplicity. If there are more, you can do 2 at a time. You can apply the result from the first 2 to the third, similar to GCD. So just a reminder to put the task statement up again. You want to find z, where z mod x is equal to a, z mod y is equal to b, and x and y are co-prime, which is like, that's given. That has to be part of the input. So let's make the first equation true. So let's use the form to say that z is equal to some value c times x plus a. Note that we know x, we know a, so if we can find c, that gives us the answer. Now let's plug it into the second. We're saying cx plus a, which is z, modulo y is equal to b. And we're going to solve this equation because we know cx plus a will satisfy the first, so we need to satisfy the second. We subtract a from both sides. And now this is cx mod y, which is equal to saying cx is equal to b minus a mod y. Now, what if b minus a was 1, right? Then what we can do is we could simply find the modular inverse of c. Since we know x and we know y are coprime, which is part of the input, meaning that we can use the extended GCD algorithm to find the modular inverse of c, or the modular inverse of x. But what if b minus a isn't 1? Well, it turns out we can do it for 1 anyway, and then if b minus a is something else, we multiply both sides by b minus a. So we solve for some number d, where dx mod y is equal to 1. So let's find that d. This is modular inverse. Then we multiply both sides by b minus a. So this side becomes b minus a, and this side becomes b minus a times d times x. And so notice that we can say that b minus a times d is just c in this equation. So if we set c equal to b minus a times this d, then cx mod y will be equal to b minus a, and therefore we've satisfied our equation. So we plug z, so now we know c, we plug it back into z, and then overall the value for c is this d times b minus a times x plus a. And yeah, and then remember that d is some artificial value we got from the algorithm. So overall, d is the modular inverse of x with respect to y. Note that this is the modular inverse with respect to y. So even though it is x to the negative 1 with respect to y, z is not being modded by y, so we cannot cancel these out, because z is not being modded by anything. And so therefore x to the negative 1 is only the inverse with respect to y. So yeah. And then that's our answer. And we can take it modulo xy if necessary. So the complexity for this is the log of the minimum of x and y, because the crux of it is the GCD algorithm. Okay, there's one more thing here, and it's kind of this thing called mobius inversion, but it's like also kind of not. I've been told that this trick is equivalent to the mobius inversion. I am not exactly sure if this is correct, so you might not want to quote me on this, but it's a trick anyway for solving problems. So this is an example. You have an array, its length is up to 100,000. The array elements are also up to 100,000, which is important. You want to find the number of subsequences where the overall GCD of the elements is 1. And I linked the problem there in the description, so you can find it and submit to it on Codeforces if you want. And in fact, I'm going to make this problem a bit harder because I love you guys. So constrain all the array elements to be up to m, where m is also up to 10 to the 5th. Now, instead of just finding where the GCD of elements is 1, I want you to find it for all of the numbers simultaneously. So for each x from 1 to m, find the number of subsequences where the overall GCD is x. So here's an example. N equals 5, m equals 6, the array is this. All the elements are between 1 and 6. So let's try something. And then you can read ahead if you want. But we're going to say that f of x is equal to the answer of x. So for example, f of 1. Well, there are 5 numbers that are multiples of 1. So what if we think about it like, we can take any subsequence of these 5 numbers except for the empty one, and that will work. And so there are 2 to the 5th subsequences, and we subtract 1 because there's one subsequence with no elements. But the problem is that could count things that we're taking the multiples of 1, but maybe the GCD is a multiple of 1. So that might count something like a subsequence, for example, just 2 or just 6, or the subsequence 2 and 6. And so the problem with it is sometimes it takes subsequences where the GCD is greater than that number, and specifically where the GCD is a multiple of that number, because we're only using the multiples of that number. So this gives us not f of x, which is what we want, but it gives us some other function g of x, which is the sum of f of x over all of the multiples of x. So for example, g of 1 is f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6. And g of 2 is f of 2 plus f of 4 plus f of 6. It's all the numbers that are multiples. And we're not stuck here. This works because we can get f of x by subtracting out everything else from g of x. Like we know, for example, g of 2 is equal to f of 2 plus f of 4 plus f of 6. So move 4 and 6 over to the other side, and we get that f of 2 is equal to g of 2 minus f of 4 minus f of 6. So we need to know f of 4, but luckily 4 has no multiples because its 8 is bigger than m, and any multiple of it will be bigger than m. So that's sort of an important detail, that when we're doing this, we need to compute from highest to lowest, because f of 2 will rely on numbers bigger than it. So we need the numbers bigger than it to be correct before we try to compute f of 2. And the easiest way to do that is to go from largest to smallest. So that's it. We can subtract out the multiples. And then we just get f of x immediately. So that's just our answer. I'm not sure if this is the only usage of Mobius inversion. I'm not really sure, again, if this is the right way to define it. But this is all I know, and it's all I've been told, etc. Right. There's one final caveat. Can we actually subtract out the multiples? And the answer is yes. It is not O of n squared, even though you have n numbers and you might be doing n operations. Because subtracting out all the multiples of I is O of m over I. And as it turns out, that sum is called the harmonic series, and in total it's m log m. And the proof for that is in the description. I linked it. I linked a lot of stuff in the description. So for this, we also need to count. So like that means that the subtracting will work. We also here, we need to count the number of multiples of I for each I, but that can also be done in O of m over I per I using a frequency array. So we actually get this exact same sum and this exact same complexity. So overall, it's still O of m log m plus n, but whatever. And yeah, this video, I actually thought it ended up long because my script was really long for it, but then it turns out that it's actually like shorter than I thought. So maybe the slide wasn't necessary, but whatever. I'm trying new stuff out. So there was a lot of content. It did take a lot to plan out, especially because a lot of it was stuff I wasn't familiar with. Like, you remember how I had you derive Chinese remainder theorem? Like, I had to derive it myself because I didn't know before this stream. And so maybe there's some better way than the equation I gave you, but the equation I gave you is sort of how I derived it. And in some ways it might be better because now I sort of understand the thought process behind deriving it, so I can explain it better. And it's sort of a tangent into why teaching might actually be a good way to learn, but I'm not going to talk about that right now. Yeah, that's it. So there's a stream soon. Again, exact time in the description. Do the problems. I think the concepts I went over here are enough, although some of them might have a bit more some of them might be a bit more involved. And yeah, bye.